Welcome to your first assignment. It's me again, Burkhard. You've already met me either via the video on the website or at Caulfield at the orientation. I'm here to talk a little bit about the assignment. It's a tricky one. It doesn't look like it because it's about cubes, right? It's just about cubes. I mean, they don't get much simpler than cubes, three-dimensional shapes. So, I mean, we've known them from primary school. Basically the whole world is built of cubes. It's surrounded by cubes, right angles. Why would you possibly want to do anything about cubes? Well, there are some subtleties, and you'll find out in this assignment. So what we'll focus on is slicing cubes. You can slice cubes in many, many different ways. So you can slice them like really close to the corner or more in the middle, and then it also depends on the orientation. You get different cross sections, different shapes. And the ones that we're focusing on in the assignment are actually ones that you can find in real life. So for example, the first one is slicing close to a corner here, and what that gives is something like what you can see on Swanson Street. So there's a corner sticking out of the pavement. That's basically it. The second one you can also find here in Melbourne. It's this Rubik's Cube-like structure. It's 5x5 Rubik's Cube sunk into the ground. Right? You can actually think about why the one at the Melbourne Museum is not a Rubik's Cube. It cannot be a Rubik's Cube, but it looks like it. Then the third one is also based on a real cube. I actually don't say so in the assignment. I should have maybe. It's Madison Cube Gardens, and that features in quite a few Futurama episodes, so you might want to check out that one too. Okay, so 3 real cubes, and we want to really make sense of them. Okay, so let's have a look at the first one. So the first one is slicing the corner of a cube. That's basically that picture there. It's a pretty straightforward exercise. The only tricky part, where people usually don't know what to do, is when I ask, well, what's the 2-dimensional counterpart of this 3-dimensional setup theorem, or whatever you want to call it. So let's just have a really close look here. Okay, so we've got a cube, we've cut off a corner, and we've created a 4-sided pyramid, and it's got sides. Maybe we call them A, B, and C. And there's also a 4th side, which is basically cross section, which is D. Okay, so it's for T, so D. And then what you're supposed to show is that A squared plus B squared plus C squared equals D squared. If we take those letters to mean areas of the respective triangles. Okay, so far so good, right? So for example, you can use, if you've got the areas of A, B, and C, then you can calculate the area of this much more complicated triangle D. Okay, so what's the 2-dimensional counterpart of this? Well, I can't really tell you, but what I can do is I can show you kind of a similar setup and show you what I would do there. All right? So a similar setup goes like this. We'll start with, we'll start with a rectangular prism this time. So it's just basically just a break, right? So here's the break. Okay, so there's the break. And in that break, we have a diagonal. So there's the diagonal, we call it D. And now to figure out the length of the diagonal, you actually only need the sides of the break, which is A, B, and C, and then it fits together just like that one here. So A squared plus B squared plus C squared equals D squared. But here, it's all about lengths. There it's about areas, right? So there's lengths, there's areas. So it's different. It's a different thing, but that's true and that's true too. So what's the 2-dimensional counterpart of this one here? Well, basically what you want to do is translate all the objects that you see here into the 2-dimensional setting, plane setting. So the 2-dimensional counterpart of a cube is a square. All right, so let's just do this. So here we've got a square, or let's say a rectangle really. Rectangle is not a square, it's a rectangle. So there we've got a rectangle. Now, what other objects do we have up on top? We've got a diagonal. So we've got a diagonal of a break on top. So what's the counterpart? The diagonal of the rectangle. So there's the diagonal of the rectangle. Let's call that C. We've also got we've got 3 sides to this brick. We've only got 2 sides of the rectangle, so we've got A and B. All right, and now what's the formula that relates C and A and B? Well, obviously it's Pythagoras theorem, right? So you see a right angle triangle in here, and that means that A squared plus B squared equals C squared, right? So the two-dimensional counterpart of this three-dimensional theorem is just Pythagoras theorem in a special setting, right? So basically, instead of talking about right angle triangles, you say in a rectangle, the square of the diagonal is equal to the squares of the two sides. So that's all there is. So that has been the exercise. That's what you have to do. And now we have to try and do the same sort of thing for this sort of setup. So just translate all those different components and see what you get. Right? All right. And again, you don't have to go overboard. Basically, if you show that you've made an attempt to, you get full marks. All right. Now the second setup is about a cube that has been sunk into the ground. So that's basically my Rubik's cube sunk into the ground. And I've actually got a little bit of a model here. So I just want to show you the model. Right? So that's the model of what you see there at the measurements. I actually went out there and took the photos myself and did all the measurements. So it's pretty accurate. It's pretty accurate what's happening there. Right, approximately anyway. So what have we got here? We've got a cube sunk into the ground, and what I'm telling you is the coordinates of this corner here and the coordinates of that one here. So basically the furthest point on top and the furthest point on the bottom here of this top square. That's what I'm telling you, and now you have to figure out all sorts of different things. So for example, how long is this, right? I have to figure out what are the coordinates of this point and that point. What are the coordinates of this point, and that point? What's the area of this bit at the bottom? Just have a look at it. What does it look like? Maybe that helps. And then you also have to figure out, well, what's the volume of this part here on top? And, well, you really have to think about it a little bit, but remember, it's all about cubes. It's all about right angles, so, dot product, vector product. I mean, they're just geared towards solving problems about these sorts of structures. So, for example, well, what's on top here? It's a square, right? So, for example, if you wanted to, if you've got these two corners here, then it's very easy to construct this one here. So you've got two sides, and you need something that's perpendicular to this. Anyway, give it a go. If you've run into any problems, you can always ask me or David what to do, and we're happy to, give you more hints. But first, give it a go yourself, okay? Now the last one is about Madison Cube Garden, as I said, right? So here, what we do is we grab the cube like this. Actually, it's quite interesting what happens when you spin this. But anyway, we don't spin it. We'll just sink it into the ground, halfways. So really halfways in. And we're interested in the cross-section that we get here, the shape of the cross-section, which might be actually quite surprising it is quite surprising for most people. And then we also want the shadow of that part above. Now, some people find that hard to visualize, so what I recommend you do, like with the whole exercise really, if you find it hard to visualize, build a model or grab a cube and really look at it and try to identify what's going on here. So in this case here, if you really want to find out what the cross section is and you just can't see it, well, just grab a cube and sink it into water, right? Just halfways, and see, well, what does it do here? So that gives you some idea of what to look for, and then you just have to do the maths. Okay, so I think that's good enough as a first introduction to this, and good luck.